Hello, everybody, and welcome to Regression in Stata. My name is Chip O'Connell. I am the research assistant for KIPSR. KIPSR is the Quantitative Initiative for Political and Social Research. Throughout this school year, KIPSR brings in various guest speakers from other universities, and we also host introductory workshops on statistical software. We're mainly targeted at the social sciences, but we also welcome anybody from any field who's interested in quantitative statistical methods. If Kipser sounds like something that might interest you and you want to learn more about us, please check out our Facebook at facebook.com/Kipser. And before jumping into this video, I want to say a couple other things. First, if you're not familiar with Stata, I would really encourage you to first watch our Introduction to Stata video. You can find that video at our website at kipser.as.uky.edu right here. And the other thing I want to say before starting is that this video is intended to show you how to apply regression in Stata. It's not intended to teach you the theory behind regression. And in this video, I assume that you already have some base knowledge of regression and the theory behind regression and the assumptions that go into OLS regression. Okay. And so with that, we can start. The first thing I want to do here, looking at my Stata do file here, is I want to tell Stata what version I would like to use. I'm going to tell it to use version state 15. And then just to be safe, I want to go ahead and clear everything, make sure all the data and all my memory is clear. So I'm going to clear all. And then the next thing I want to do is bring in some data. So I'm going to use this kind of stock Stata data set that has information on various makes of automobiles. I will show you this. Let's take a look at this. If we look here, it's got various makes of different automobiles along with their price, their miles per gallon, their repair record, and various other variables on those makes of automobiles. And so let's say that we want to predict the price of an automobile. In order to do that, we should run a regression with price as the dependent variable. And in order to run just a simple univariate regression, what we can do is we can type reg, R-E-G, for regress, our dependent variable, which in this case is going to be price, and in this case I'm going to use MPG as our one independent variable. So I will run that. Stata will spit out this output. Kind of a couple important things here. Over here on the right, Stata will tell you, the number of observations. It will give you an F score. It will give you this goodness of fit measures in the R squared and the adjusted R squared. And if you're doing hypothesis testing, the two numbers that you probably really care about are these coefficients and the p-value. And so in this case, what this is saying is it's that the coefficient on MPG is negative, which means that miles per gallon is negatively related to the price of a vehicle, and this is statistically significant at a very low level. All right. But in order to get a better model, we're going to want to run a multivariate regression. We're going to want to add other independent variables, other control variables. And in order to do that, we just reg our dependent variable, and then we just list our independent variables after that. So we can run this line. And it spits out a really similar output, except this time it's added our other two independent variables. If we look at this model, this time MPG is actually positive instead of negative, but this time it's also statistically insignificant. Weight and foreign are both positively related to the price of the vehicle, and they are both statistically significant. We can also it's probably a good idea to compare our R squareds. And so the R squared here is about 0.49, almost 0.5. So this model is explaining about 50% of the variation in the price of our vehicles. If we can compare that to the first model, the R squared up here was only about 0.21, 0.22. And so this second model with the additional independent variables is pretty clearly a better model, has a better fit than the bivariate or the univariate model that we did before. We can also run interactions between variables. The way to do that is by adding this hashtag between two variables. So say we want to interact miles per gallon with the weight of a vehicle and see if the interaction has any effect on the price of a vehicle. And the other thing we need to do is tell Stata that these are both continuous level variables. All right, and the way we do that is by saying C dot for continuous, C dot miles per gallon, hashtag C dot weight. They are both continuous variables, so they both need a C dot before them. And so we can run this. Notice that Stata gives us includes both the parent terms as well as the interaction term here. And we can look, this interaction term is almost significant at the O5 level. Depending on your field, you might call that significant, but I'll leave that up to you. And we can also run an interaction between two categorical variables or a continuous and a categorical variable. The way to designate a categorical variable is to put an I dot instead of a C dot. So this is two continuous this is a continuous and a categorical variable interaction. So we have C dot weight for continuous, hashtag I dot foreign for categorical. And we can run that. And you can see it gives us a similar output. Okay, so now that we've run our regression, there are a couple things we might want to do post-estimation. So I'll show you a couple post-estimation techniques. Let's run our regression again. The standard output for a regression, as I've already talked about, provides a goodness of fit measure in the R-squared and adjusted R-squared, but you might want to look at other goodness of fit measures. We can do that by running eStatIC. If we run this, this will give us the AIC and the BIC, the information criterion. We can compare those. That's just another goodness of fit measure. And another really useful kind of post-estimation technique is the predict command. The predict command can predict a whole host of things. I would encourage you to check out the help menu with predict. But one thing that you probably want to predict are the predicted values. So the default with predict are the predicted values. And right here, I'm telling it to predict a new variable called y. And because I don't specify anything else, it's going to make a new variable called y that are my predicted values from this regression, the regression that I just ran. Okay, so we can run that. But again, you can predict a whole number of things with this predict command. And another useful thing might be the residuals. So we might want the residuals from this model that we just estimated. So in order to do that, I'm going to say predict a variable called e, and then I'm going to put comma for options, and then I want R for residuals. So predict E, comma R will predict my residuals in a new variable called E. And so if I go look at my data, right here is a new variable called Y that is the predicted values from that previous regression. We can compare it to the actual price values. Over here is the residual in a new variable called E. And just as an example, so our predicted value is about 4,770 something. The real price is 4,099. That gives us a residual of negative 679. And another kind of useful command is the test command. This will do a wall test to tell you if two coefficients are equivalent or not. And so if we run this high p-value here tells you that these two these two coefficients are actually not equivalent. One is bigger than the other. And now, in order to make sure the regressions that we just ran that the coefficients that we just obtained from the regressions we just ran, we need to make sure that those coefficients match up with the classic OLS assumptions. Okay, so I'll show you how to check those in Stata. The first assumption we're going to check here is that our residuals are normally distributed. Okay, so in order for these coefficients to be considered blue, in other words, best linear unbiased estimators, they have to meet these assumptions. And one of them is that the residuals from the model must be normally distributed. Another way that people sometimes say that is that the residual should add up to 0. Okay, and so one way we can check that is we can do a Shapiro-Wilks test on that E variable we just predicted, that residual variable we just predicted. And so we can run that, and that'll tell us whether or not this variable is normally distributed. We can also look at it graphically by plotting a kernel density plot of our residual variable and putting a normal line over top of that plot. So if we run that, that'll give us a graphical depiction. And so if we look at this, it's almost normal. It's certainly not perfectly normal, so you might want to think about transformations, but it might be okay. So it's almost normal looking at it graphically. Right. The next assumption that we're going to check is checking for linearity. So OLS regression assumes that the relationship between the independent variables and the dependent variable is linear. And so kind of a rough way of getting at that is to just run a scatter plot between the dependent variable values and the independent variable values. So we can look at that. And if we look, this is close to linear. Close to linear. If a more refined way of looking at this is to do the same thing, but tell Stata to give us a lowest smoother over it. A lowest smoother will run a regression of MPG on price and show us the fitted values, give us a smooth curve of the fitted values. And so again, that's almost linear. We can kind of see almost a slight U-shaped pattern here, so you might want to think about running, a quadratic model or a formula or a curvilinear model, but it's almost linear, right? Now the problem with doing this a dependent variable and one independent variable at a time is that when we run those scatter plots, those don't take into account the other models in the variable, the other control variables in the model. So if we want to check linearity with all models in the model, we can do an augmented component plus residual plot. So we run that. And so what we're really looking for here is we would like this, our lowest smoother here, to be more of a straight line. And so again, it's almost linear, but not quite. We can see kind of a little bit of a pattern here. So you might want to look for some other transformations here, but again, it's almost linear, so it might work. Okay. And we also want to check for unusual or influential observations. Okay, so in order to do that, we're going to generate a new variable called observations, and it's going to be equal to underscore n, which means it's going to be equal to the observation number that Stata has for that observation. So we'll run that, and then we're going to predict standardized and student residuals for each of our observations from that previous model. So we can do that by predict standardize and say we want standardized and student residuals. So we'll run both of those. Those will give us our two types of residuals. And then we can run a scatter plot that puts the residuals against the observation value. Okay, and kind of the rule of thumb here is that visibly distant observations or values greater than 2 may be problematic. So let's run each of these at a time. These are our standardized residuals. And so if we look at this, 12 and 13 as well as 28 are above 2. They're kind of visibly distant from the rest of them, so those might be a problem. We can also look at the student residuals. And again, 12, 13, and 28 are giving us problems. So we might want to look at those observations. We might want to consider dropping them from the model. But again, we want to really strongly consider what's going on with those things and why they're having so much influence. We can also predict our hat values here. So we can predict those and then scatter those against our observation variable. And what we see here is that observation 71 is clearly having a lot of leverage. And so we're going to want to take a look at that and see what's going on with that variable. And we can also predict our Cook's D scores and our DFIT scores. So let's predict both of those. and we can scatter those. For the Cook's D here, observations greater than 1 might be problematic as a general rule of thumb. So we'll look at that. And so again, 13 here is having some influence, so we might want to look at that. And we can look at the DFIT score as well. And again, 13, again, is having some undue influence here, so we want to check that. One other assumption that we want to check is that our residuals are not heteroscedastic. That means that the variance of the residuals is the same throughout all values of the model, of the dependent variable. And so in order to check this, we're going to run our regression again. And we can run this Broich-Pagan test using EStat het test. We can run that, and that'll show us heteroscedasticity for the whole model. And so, statistical significance is evidence of heteroscedasticity here. So we do have some heteroscedasticity problems here. And we can also check one variable at a time by listing the variable after het test. And that'll show us each variable. I'll run these other two. We can also use Schroeder's test as another test of heteroscedasticity. Or we can look at it graphically by looking at a residuals versus fitted plot with the RVF plot function. And again, kind of the rule here is that any discernible pattern can be evidence of heteroscedasticity. And what we see here is that the variance of this thing really kind of explodes at the higher values of our dependent variable here. So we definitely have some heteroscedasticity problems with this model that we're gonna want to take a look at. One more assumption is multicollinearity. None of your independent variables should be correlated with one another. The way to check that is with the pwcore command. So we're going to say pwcore plus all of our independent variables. We'll run that, and that will give us a correlation matrix. And if we look here, we definitely have some correlation problems as well, because weight is highly correlated with miles per gallon. Foreign and weight are also pretty highly correlated. So we do have some multicollinearity problems here as well. So we might want to drop one of those variables or maybe transform it so that it's not so collinear with one of the variables, something like that. We can also look for multicollinearity graphically. So you can tell it that you want a matrix graph of all of these independent variables, and I always like to specify the half command here. I think it makes it easier to read. And so we'll look here, and you're really looking for linear patterns here. And again, all of these are showing that we have some multicollinearity problems. And you can also look at the VIF factor, the variance inflation factor with EStat VIF. The lower the VIF, the better. General rule of thumb is that 2 is too much. I've also seen cutoffs at 4 or even higher, but again, depending on what your field does. And then two more assumptions that we need to look for here are omitted variable bias. So we can look for that with the OV test, EStat OV test. And the null hypothesis here is that the model has no omitted variables. We can pretty clearly reject that null hypothesis. So this regression we ran does have some omitted variable bias, and we need to find some other controls and other things to have a really good model to predict the price of a vehicle. And then one other assumption is that each observation should be independent of another. And if we have time series data, that may not be the case. We might have serial autocorrelation. So I'll show you how to check for that. To check for that, I'm gonna bring up a different data set. I'll show you this data set. This data set just has the quarterly date as well as GDP. Also has housing starts, the unemployment rate, and a few other variables here. So the first thing I want to do here is tell Stata that this is time series data and that the Q date, the quarterly date, is the time series variable. And I'm going to tell Stata to TS set, time series set, this data set based on Q date as the time variable. All right. And then I'll run a regression of unemployment rate on GDP. We see that this is showing us that GDP is positive, but it is not a significant predictor of the unemployment rate. But we probably have some serial correlation problems here because this is time series data. So in order to figure that out, we can first take a look at it graphically. So again, we're going to predict our residuals again, and then we're going to scatter plot those residuals against the quarterly date. And we really want to see no relationship between the error term and time. And what we see here is a pretty clear pattern between our residuals and the time variable. So there's definitely some serial correlation problems going on here. We can also test for serial correlation statistically with the Durbin-Watson statistic. That's E stat D Watson. And the Roish-Godfrey test is another test for autocorrelation. We can E stat B Godfrey. And there's also Durbin's alternative test with E stat Durbin alt. We can also use these commands to test for higher order autocorrelations. So we can do that with the lag option. So we can E stat B Godfrey lag 1 through 5. And this syntax will give us a Roish-Godfrey test with lags going back 5 time periods. And so it gives us the lag going back 5 time periods. If we look, they're all significant here. So we have significant autocorrelation problems here at a higher order than just autocorrelation 1. All right. Stata can also check for spatial autocorrelation. It's a little bit more complicated, but if you're interested in this, I would point you toward the SP set, SP matrix, and SP regress commands. And now I'm going to show you how to fix a few of these assumption violations. First is heteroscedasticity. It's a fairly easy one to fix. We can just run robust standard errors. And in order to do that, you just run your regular regression and then comma robust. And this will give you robust standard errors, which should take care of any heteroscedastic problems. Oh, sorry about that. I need to bring in our auto data set again. And then run our regression with robust standard errors. You can also cluster your standard errors by a variable group. So for instance, we can cluster our standard errors based on whether or not the automobile is a foreign-made car or a domestic-made car. And the way you do that is just cluster parentheses the variable that you want to group by, in this case foreign. And then we can also have kind of more advanced standard errors, bootstrap and jackknife standard errors. So to run a regression with bootstrap standard errors, you're going to say bootstrap regress your independent variables and your dependent variables. So we're running that. The default for bootstrap is 50 iterations. If you want more iterations, you can specify how many reps you want. So you can say bootstrap comma reps. In this case, we'll do 500, and then our regression command. With 500 reps, it significantly takes a little bit more computer power than the default 50 reps. So this might take just a second. But there we go. And then you can also do jackknife standard errors by just putting jackknife and then your regression command. And now I'll show you how to fix a couple ways to fix autocorrelation. So we'll bring back this data set and we will TS set it again. And then originally we ran a regression on the unemployment rate and GDP, and we saw that we had correlation problems there. One way to take care of this is by including a lagged dependent variable in the model. And to do that, you can just do L dot the dependent variable. So it's regress our dependent variable unemployment rate, our independent variable GDP, and then our lagged dependent variable, which is being included here as an independent variable on the right side of the model. And then the default L here is going to lag it by 1 time period. So that's a time lag of 1. And what we see is that that time lag of 1 is a significant predictor, and so, we did have autocorrelation problems there. We can include higher order lags by specifying L1, L2, L3, and so on. Or we can just specify L1 through 5, 1/5, 1 through 5, dot the variable. And that will give us 5 higher order lags. Okay. And then another common way to take care of autocorrelation is by first differencing. So we can run a regression where instead of using our normal variables, we're running the first differences of those variables, which would be the value. So it would be the value of the unemployment rate at time period 1 minus the value of the unemployment rate at time period -1. Okay. And the same with our independent variable. And that's kind of a common way to draw those time trends out of the data, and so that we're just looking at a year-to-year change, and we don't have so that we don't have those autocorrelation problems. You run that. Okay, so that is how you run a linear regression in Stata, and ways to check the assumptions and make sure that you're not violating any of those. Before I sign off here, I will show you some other common models and how to use them in Stata. I won't go into the details of how to check the assumptions on these. Most of these have pretty similar assumptions to OLS. Some of them have fewer. Most of them have fewer. And you can kind of check the assumptions in the same way, but I would encourage you to do a little bit more research if you're going to be using these models. But just to show you, let's bring in our auto data again. And so if you have a binary dependent variable or a dichotomous dependent variable, 0, 1, you're going to want to run either a logit or a probit. And so in order to run a logit, we're just going to say logit, our dependent variable, followed by our independent variables. And this will run a logit model. And so we can see that price is positively correlated with the chance of it being a foreign-made car, and it's statistically significant. Weight is negatively related to the chance of it being a foreign-made car, and it is also statistically significant. We might also run a probit. The command for that is just probit. Or you might want to run a complementary log-log regression. The command for that is clog-log. And if you have a small data set, or you have a dependent variable that doesn't appear very many times in the data set, you can use an exact logit regression. The command for that is xlogistic. And then a couple other commands that you might want to check out are first logit and rare events logit, relogit, that do similar things to the exact logistic regression. Stata can also handle ordered models. So we can do an ordered logit with O logit, or we can do an ordered probit with O probit. I'll show you an ordered logit here. And a multinomial logit. Just bring in this data set with a multinomial variable and show you the multinomial model. Okay. And Stata is also capable of doing various kinds of count models. So let's bring in a data set with a count variable. It can do a Poisson model. The command for that is just Poisson. It can also do a negative binomial regression. The command for that is nbreg. And it can do Tobit regressions, truncated regressions here. Stata is pretty powerful. It can do a lot of different models. It can do Heckman selection models. I can show you what that one looks like. We can do duration and survival models. I'll show you these. One thing to note if you're doing a duration or a survival model is this command stset. So it's similar to the tsset command that we saw earlier, but this is actually survival time set. So if you're going to run a duration model, you need to run the stset command instead of tsset, and that designates this data as survival data. We can run a non-parametric Kaplan-Meier curve to see if there's a relationship here. And then we can run a Cox regression with the command stcox. Um, and then kind of last here, Stata can also do GLM models. So kind of this is the syntax for GLM regression or a linear regression. Here's the syntax for a probit regression. And Stata is capable of handling many, many other models. You can do multi-level models in Stata. You can do simultaneous equation modeling in Stata. Stata is really capable. I'm not going to show you all of those now. But if you're looking to do more advanced modeling, Stata is definitely capable of handling those. And so I would encourage you to read the help PDFs and things in the Stata online community about those things. And yeah, so if that's kind of the end of this video. If you've enjoyed this video, again, I would really encourage you to like the Kipser Facebook page, give us a like there, as well as check out our website here. And thank you for listening, and I hope you enjoyed this. Thank you.